This is merely a reference to the fact that opposites attract. They've got the positive ions attracted to the negative ions. Let's just move on. So this chapter is all about chemical bonding. Chemical bonding is what causes atoms to stick together, and they're going to fall in 2.5 categories. One category is pretty much the same as the other. But anyway, today we're going to, oh, that's not true. We don't have the polyatomic ion quiz too. We already did that. We bought ourselves a little bit of time. Here is the approximate schedule for the next couple of days, terribly written by me. Today's the 10th. We're going to try to knock out the notes on chemical bonding. Your homework's going to be worksheet 1. Big shock there, right? And then next time, we might need to finish up some notes. Next time, we'll probably be building models also. You guys will get some model kits out, get to connect some balls together with sticks and stuff. And the real purpose of that is to see the 3-dimensional shape of molecules. And there's 5 shapes we're going to deal with. I think I brought them up to you a couple weeks ago. Linear, bent, trigonoplanar, trigonal pyramid, and tetrahedral. We'll take a look at those today because those all just sounded like gobbledygook words, didn't they? It's actually a 2-day lab. We start it one day, we continue working on it the next day. The 3-dimensional nature of matter is really what we're dealing with in this chapter. Before we get too started, we have to kind of review some of the ideas we must know. How are we going to figure out the valence electrons for any element? We count like an idiot. How do we count? 1, 2, 3, 4, 5, 6, 7, 8. That 2 drags across because they still have 2 valence electrons. So let's assign these to a couple people. Noah, I want you to tell me how many the alkali metals have. Let's go, Angel. No. Angie, how many does hydrogen have? Sophia, how many does halogen have? So you just grab your periodic table and you count across, right? Noah, how many valence electrons do alkali metals have? 1. Because you go 1, and you're there, and you're done. Okay? Angel. Yeah. How many does hydrogen have? Also in the same column. How about the halogens? 7. 8 is the last column. So a lot of times people, when they get to the other side, they'll go 8, 7, 6, 5, 4, and they'll go backwards instead of counting forwards. They'll start at 8 or backwards. If we have a charge, how's that going to change an electron configuration? So sodium's got a +1 charge. Are we adding electrons or removing an electron?
Removing.
So we're just going to take the last electron, also known as the valence electron, off. If it's got a negative charge, we would add 1 on. On the periodic table, you have to know the difference between the metals and the nonmetals. Be a finish on your periodic table. It says right here on your periodic table, metals and nonmetals right underneath polonium and astatine. And it tells you which direction is which. Are there more metals or nonmetals on the periodic table?
Metals.
There are 85 metals to about 13 nonmetals. Lots of metals, okay? Most of the periodic table is metals. Let's just circle the nonmetals. You tell me what to circle. Should I circle sodium? I actually need to get in pencil mode here. Get enough ink in my finger. Should I circle bromine? Is it a nonmetal? Yes. Is titanium a nonmetal?
No.
And to find it, see if it's a nonmetal or not, you only need to go to the back, right? You only really need to search that little triangle of nonmetals, because if it's not in that little triangle, it's on the other side. Nitrogen's obviously, it's already circled. Oxygen, calcium. So calcium's a metal. We have metal in our bones. Yes. Zinc's a metal or non-metal? Metal. Phosphorus? Non-metal. Fluorine? Barium? Aluminum? Yeah, but it's right on the line, isn't it? And sulfur? Non-metal. So there's a tiny area of non-metals. And like I said, we count 1, 2, 3, 4, 5, 6, 7, 8. figure out how many valence electrons they have. And that separation between the metals and non-metals is right there. That's going to be one of the key factors in deciding things in a little bit. You're going to look and see, are elements from this side of the periodic table or that side of the periodic table? Are they metals or are they non-metals? And we're going to make some decisions as to how they would bond because of their position. So a bond is a force that holds two atoms together. It's actually protons pulling on electrons, because protons have a positive charge and electrons have a negative charge. There's a attractive force called a Coulombic attractive force, Coulomb attractive force. Coulombic attractive force that pulls on the two atoms and holds them together. And then afterwards, they behave as one unit. Now, there's two very different types of bonding. There's, I walk over and I take her electrons from her, and I have what charge now that I've taken this electron from her? Negative. And she has what charge now that she's lost her electron? And then we have opposite charges that are then like attracted to each other because opposites attract. And then there's this other one where the two elements come up to each other and I try to steal the electron and I can't steal it. She can't keep it back. And I can't steal it. She can't take it back. And we just keep doing this tug of war match forever. And we call this eternal tug of war match covalent bonding. Sorry about just grabbing your hand like that. So there's two very different types of bonding. Ionic bonding, oh, and this is, I think, two sunny side up A's. I think this is me just trying to say, hey, sometimes the electrons are stolen, and it's the electrons on the outside. What do we call the electrons on the outside?
Valence electrons.
The valence electrons are the ones that can be involved in this. Sometimes they're shared, and sometimes they're unevenly shared. So ionic bonding is the first one we deal with. And we really don't deal with it much again because it's pretty easy to kind of like conceptually deal with, but then when you get into the nitty-gritty, it's almost impossible to deal with. So we just kind of deal with it from a very light, look at the top and that's it perspective. Ionic bonding is between a metal and a non-metal. So they have to be on opposite sides of the periodic table. And the nonmetals are the strongest elements on the periodic table. They steal electrons from anyone else they can. The nonmetals are the strong ones. The metals, shockingly, I don't know what that noise was. Is that a shoe squeak? I thought there was a duck loose in the classroom. Would be kind of neat for about a second. The metals are actually the weak ones, and they don't have good control over their electrons. What type of elements conduct electricity? Metals. They conduct electricity because they don't have good control over their electrons. So their electrons can move around. So in ionic bonding, the nonmetal takes the electron from the metal, and then they have a charge afterwards. And this is about the beginning and the end of the ionic bonding conversation. The whole rest of the discussion is going to be covalent. The real focus of this chapter is covalent bonding. Are there any questions on ionic bonding? Because we're going to spend the next 45 minutes just talking about covalent bonding. It's a lot more complicated than that, but we just don't go there. All right? So the metal loses the electron, the non-metal gains the electron. If we take a look at the configurations, this was sodium. This was chlorine. Oops, no charge. Sorry, chlorine. We don't have a charge yet. And when sodium loses an electron, it loses that one. What is left? What does it look like after it loses that electron? What element does it look like after it loses that single electron?
Neon.
Looks like neon. This is a configuration just like neon. And then chlorine stole that electron and now has a 3p6 on the outside also. And it looks like argon. And so they are still trying to look like noble gases. The nonmetals are just strong enough to strip the electrons off from the metals in the process. With covalent bonding, it's two nonmetals. We say they're sharing. So the nonmetal comes up to the nonmetal and says, hey, I'm strong and so are you. Pull as hard as you can. That's pretty weak. You gotta pull harder. Pull harder. As hard as you can. Okay, that's pretty good. All right? And so they pull and pull and pull, and no one ever wins. We pretend this is sharing. Okay? If I'm strong enough, I would just take the electron, right? Like, I have his head. Just tear it off. But I can't, so we end up sharing these electrons. We still have the same goals to look like noble gases. Neither one of us look like Medi over there, the noble gas. We unfortunately look like this, don't we, Team Alkali? Yeah, that's a motley crew. And they are going to share electrons, though, to try to look like them. If hydrogen, well, how many does hydrogen have? If it shares with another hydrogen, it would have two. And who would it look like when it has two?
Helium.
And so it's going for that same noble gas configuration, in this case helium. Chlorine has 7. It needs to share one with another chlorine, and then they would both have 8. Almost all of our molecules are going to go for either 2 or 8. These are going to be our two primary goals, is to get to 2 electrons, like helium, or 8 electrons, like the other noble gases. And 8 is so common, it'll even have a cute name called the octet rule. Yes, ma'am.
So their goal is to look like noble gases when it comes to covalent bonding.
Yep, or ionic. Ionic are also trying to look like the noble gases.
So
with ionic, the nonmetal is strong enough to just steal the electron. Yesterday I broke a girl's pen in her hand. I went to grab the pen and it just like sheared apart. And it was like, oh. Turns out she had stolen my pen. It was actually my pen. But even in ionic bonding, I'm stealing the electrons so that I look like a noble gas, and that results in the other element looking like a smaller noble gas. In covalent bonding, we're sharing to get to that because we're not strong enough to steal from each other. Like two bullies eyeing the same peanut butter sandwich. We're like, well, let's just share it. And then they just keep staring at it forever because neither one of them is strong enough to take possession of it. So it also elucidates why some of these elements brings light upon. Why some of these elements are so reactive with metals and things, because like chlorine is forced into sharing with another chlorine if there's no one else to react with. Is it safe to breathe in chlorine gas? No. You breathe in chlorine gas, reacts with the water in your lungs, and turns that water into hydrochloric acid inside your lungs. Alone, chlorine is stable. When it has other elements to react with, it will. And because it's sharing with itself to get to 8, but if there's someone weaker to steal from, it will. Sometimes you have to put a little energy in to get those reactions going. There's lots of combinations we're going to see. Sometimes we might attach a couple elements to the element in the middle, like nitrogen there. Nitrogen has 5 electrons on the outside. How far away is 5 from 8?
3.
3. That's going to be some of our higher level math. It's kind of going, nitrogen has 1, 2, 3, 4, 5. It needs 3 more. And then kind of making enough connections that it gets to 3. Carbon has 4. This I already know, see it has 4 dots there. But we could figure that out also by going 1, 2, 3, 4. How many more bonds would carbon need to get to the magic 8? 4. And so it makes bonds until it gets to 8. Now, a term that was briefly discussed last chapter but not quizzed upon is electronegativity. Electronegativity is actually when we share electrons, Who is strong? Oh, she's actually stronger than Michael. When we share electrons, which element pulls harder on those electrons? The relative ability of an atom and a molecule to attract shared electrons to itself. So we're sharing electrons. Sometimes with definitions, you have to start at the end and go in reverse. Have you started doing that yet? These long sentences and kind of go, what the heck is going on in this definition? So we're sharing electrons. I'm attracting those electrons to myself. The ability of me to pull electrons to me. Okay. This sounds like a fun lab where we walk around and we do like a mini tug of war match. I get like a tiny rope out. And Sophia and I both grab the rope and we pull and we see which way we go. And we rank everyone. Okay? We rank everyone from Michael to Sophia, right? Sorry, Michael. And every one of you would rank somewhere in there. Some would be like, I'm at the middle, that's okay, at least I'm not at the bottom, right? There'd be like that one person would be at the top. I'm gonna go with Solomon back there. Okay? Although you don't feel too hot, do you? But, maybe Justin, I don't know. And so there's actually a trend that's very similar to our previous trends. The smaller an atom is, the stronger it is. The bigger an atom is, the weaker it is. Who's the weakest on the periodic table? And in this classroom, that would make it Vaden, because Vaden, you're the farthest back on the periodic table in the first group. So Vaden would be the weakest. Take a look at this periodic table and figure out what's missing. Quite hear any of those words. It sounded like. Who's missing from the periodic table?
Helium.
Helium? The whole column missing, isn't there? These are the noble gases. That's these guys over here. You come up to Mehdi, you stick your hand out to shake it, and he doesn't stick a hand out in return. He ignores you. No. Listen to the words again. I stick a hand out, and you don't in return. You ignore me. So just ignore what I'm about to do. He shakes his hand. Oh. The noble gases do not bond ever. So how can they attract shared electrons to themselves? They don't. He's not sharing with you. He's like, my fruit cup. You get none. They're all his. He's not sharing. Same thing with those guys back there. They're not sharing. Now, you all are the most evil elements on the periodic table when it comes to sharing. Your sharing is like mine 90% of the time. You get a sip. 90 sip. I think that makes you the most evil on the table.
Yeah.
From my perspective, Lucy is fluorine, and we go all the way back to Ace back there, it's astatine, which is an extreme poison. But weird ranking scale, it's a 0 to 4 scale. All right, 4 being the strongest, and fluorine is the strongest. And then you have a bunch of other weaker elements. There is one break in the trend that you have to know, and that's hydrogen doesn't follow the trend. Notice that I wrote an H over top of phosphorus. What is the value for hydrogen? 2.1. What's the value for phosphorus?
2.1.
2.1. I'd like you to put an H over top of the phosphorus so that you know, as far as the trend goes, where phosphorus would fit in. All right? I mean, where hydrogen would fit in. It doesn't follow the standard pattern everyone else is following. And do we deal with hydrogen a lot, do you think?
Yes.
Yeah, so we have to deal with it a lot. We don't deal with gold and silver and platinum a lot, so we don't care that they're weird up there, all right? But the other elements, like hydrogen is pretty important. Who's stronger, nitrogen or hydrogen? Who's stronger, nitrogen or hydrogen? Nitrogen. So even though they might share electrons, nitrogen's a little stronger, it's going to pull those electrons to it. And it might be like a 60-40 share, not a 50-50 share, all right? Who's stronger, hydrogen or chlorine? Chlorine. Again, it's going to be shifted towards chlorine. The sharing isn't going to be equal. So what you're supposed to do is actually subtract those two values against each other to figure out how off is it. So hydrogen versus hydrogen. What's 2.1 minus 2.1?
0.
0, it's a difference of 0. So that's just going to be boring, regular, covalent, or equal sharing. I don't know the value for oxygen exactly. I think it's a 3.5.
Yeah.
So 3.5 minus 2.1 is 1.4. Okay. So the difference is 1.4. And so that's in this range here, isn't it? That's going to be unequal sharing. Still considered sharing, it's just not equal. All right, because a 1.4 is in this range. And so it's called covalent, but polar. Polar meaning a positive pole and a?
Negative.
Yeah, so let's gonna say a positive / negative pole. Not like I'm climbing a pole. But yes.
How did you get the 1.4?
We subtracted in our heads oxygen is 3.5, hydrogen is 2.1, 3.5 minus 2.1 is 1.4, according to people out there that I trusted. Subtracted those two numbers. Cool. All right. Chlorine versus hydrogen. Is there water back there? Did it spill?
No, I didn't know it was just here.
Someone
spilled something.
So there is a spill.
Yeah.
Have you just now noticed it?
Yeah.
You need help? Alright, what is chlorine and hydrogen? What is sulfur and hydrogen? What is chlorine and hydrogen? I think chlorine and hydrogen is the most extreme difference. What is 4.0 minus 2.1? 1.9? And so this one is technically ionic. Lucy is strong enough to rip electrons right off a hydrogen and then create a positive and a negative charge. Even though hydrogen's in that covalent land, you're strong enough to mess with it. You guys need paper towels? There's a bundle of them right back there behind. Hand them the paper towels. Like, stand up and deal with it. For people watching the video at home, there's a mysterious puddle over there by a bunch of boys. We don't know where the puddle came from. It's okay though, they're dealing with it now. Yes?
So covalent is when it's equal sharing, and then polar covalent is unequal sharing?
Succinctly put, yes. Covalent is when it's equally shared, or pretty close to equal. And polar is when it's not very equally shared. And then ionic is it's not sharing. It's like, your toy is mine now. Watch me play with it. I don't know what I'm playing with, but it goes do.
Rubik's Cube?
An ice cube?
Rubik's Cube.
Oh, okay. A Rubik's cube. I was like, you playing with ice cubes? Is that an ice cube back there?
Yeah.
Oh, it was an ice cube on the ground.
And water.
Well, that's what happens to ice cubes.
Yeah, they someone spilled it. They were like, ice water.
Ice water?
Yeah.
That's terrible. At least it's not like a milkshake. Ice.
A milkshake with ice in it?
So I'm actually going to pause this first video now and move on and try again. Let's. Can I get two volunteers to the front of the room? 2 volunteers. Justin, thank you. Yeah. And oh, Gavin, thanks. Come on up. Thanks. They both raised their hands enthusiastically. Okay. Okay. Justin's on this side. Gavin's on this side. All right. Like right here. We're gonna do some hand holding. There's gonna be a lot of hand holding. Pause. Okay. Right. Okay. So now, if these guys are equal strength, which way am I gonna go when they pull at full strength? Do it.
Oh, no.
Okay, so which way am I going? Nowhere, because they're canceling each other out, right? Now move forward 2 steps. That is forward, right? Okay, now pull with, which way might I go now? You see the difference? For those of you who can't see, the boys are now standing at like a 45-degree angle from each other instead of a 180-degree angle. So the angle makes a difference, right? And so now when they pull, I go in that direction because instead of working against each other, they're now working as a team, right? Okay, good, thank you. Is that so tough?
Nope.
All right. Ian's sanitizer has been applied. Awkward and sweaty hands. I'm not gonna say who. It's probably me. So polar molecules not just have the difference in the bond between the 2 atoms, but depending on how that bond atoms are angled, the one on the bottom is kind of like the second scenario. With the water, H2O there, that's H2O. I don't know if you've seen H2O before. That's H2O. Oh, you missed it.
Maybe I do it again.
No, he needs to see this. Got very physical. I took a more match. I lost. So first we did this, and this is carbon dioxide. There are oxygen atoms of equal strength. Which way am I going to go?
Stay there.
Yeah, because they're both equally strong, right?
Yeah.
Okay. However, if like water, we go at an angle and they pull. Mia has a panic attack and Mr. Murphy flies at her face. Okay, good. And so, if there's an angle, it's going to impact the distribution of electrons. Now, in reality, it's not like oxygen is getting yoinked over there, but its electrons are being shifted in one direction or another. Its electrons are being shifted. With this one, with the carbon dioxide, the electron shift is kind of being balanced out. So both of these, this molecule on the left is polar, meaning it has a positive pole and a
Negative.
Now we're never going to indicate which side is which. We are going to look at 3-dimensional models. We're going to try to figure out if the molecules would be polar or not. In this case, let me just swap these out so it's a little more obvious. In this one I'm holding in my hand, we have 2 green atoms, let's call them chlorine, 2 brown atoms, let's call them fluorine, and they're pulling on the atom in the middle, right? Is this atom going to have electrons pulled more in one direction or the other? Fluorine is the strongest atom on the planet, right? Strongest atom on the periodic table, the highest in electronegativity. So this might be like Justin and Justin, and then this might be, I don't know, coal, and Justin's stronger than coal, so those electrons are going to be shifted in that direction over the other. Okay, just slightly, not like embarrassingly so. Not like you fall down. You just go, oh. All right. I need you to jot this down in your notes. These terms don't mean anything to you yet, but by the end of the class, they'll mean something to some of you, and the other people will be exhausted and won't have a clue what's going on. Yes, you with the hand in the air.
What is the?
I'll read them to you.
Yeah.
Trigonal pyramid. It's like triangle, but a little fancy spelling. Okay. Trigonal pyramid. And bent. That's the word bent. Those 2 types of molecules are always polar. Plug your ears over there, Ashford. He's taking like the super advanced version of this on the test. Those are always polar. These 3 types of shapes, linear, you go with the word linear, tetrahedral, which this handwriting is Mr. Shangraw's, which is why you can read it at all. It was mine. Tetrahedral, tetra means 4, hedra means base, tetrahedral. And trigonal, it's the word trigonal again, but instead of pyramid, that one says planar. as in all in one plane. We learned about planes, not like the flying, but planes don't do this, Russell. Like all one plane, flat. So with the first two, any molecule that's driven on a pyramid or bent is going to definitely be polar. Any molecule that's one of these, we're going to worry about symmetry. Let me build some of those. So this is currently the tetrahedral shape. Tetra means 4. Can you see why this might be the tetrahedral if it means 4? It's got bonds in 4 directions. Is it the same in every direction? Is it symmetrical or the same in every direction?
No.
No, one direction is whatever these brown atoms are, the other direction is whatever these green atoms are, and they might not cancel each other out. It might be Justin and Justin versus Cole and Cole. And Cole is slightly weaker than Justin and Justin, and therefore the electrons are going to be shifted in the direction of the strongest atoms. If, however, it had been Cole versus Cole versus Cole versus Cole, who's going to be the winner?
Cool.
No, it's going to be a 4-way tie and they all lose. The electrons go nowhere if it's the same person against themselves 4 times. All right? So if there's symmetry, perfect symmetry means non-polar. All right, that's going to be a hard idea for us to get down. I don't expect it to stick quite yet. How to determine if a melecule is polar or not? First, we're going to check and see if there's any polar bonds, meaning, how different are they? Okay? How far apart are they on the trend? If they're really far apart, definitely be polar. If there are polar bonds, do they cancel out? So Cole might be stronger than me, and therefore the bond gets shifted to him. But if there's 4 Coles, I might get yanked in one direction by Cole and in the other direction by Cole, and they cancel each other out. So even if that bond is polar, if there's an identical one in the opposite direction, other than me being tortured, being like ripped apart like some medieval thing, I'm not going anywhere. I'm just like, oh, okay. Not being yoinked across the room. If they're not symmetrical, the word for not symmetrical is asymmetrical, then that molecule would be polar. And again, polar means it would have a positive or negative sides to it. If it's polar, it's going to have a positive and a negative side. All right. Only valence electrons are used in bonding. We're about to get to the part we start drawing lots of dots and making connections. We're going to use Lewis dot structures. Lewis dot structures is named after a guy whose last name, shockingly, was Lewis. And he came up with this system. And now it's the system that everyone uses when they draw molecules. I don't know what the old system was, because this is like 85 years old, and unlike Mr. Shankar, I don't remember that far back. So we're going to represent valence electrons as dots. Pick an element for me, Ryan. Fluorine. So we're going to write down an F, because that's the symbol for fluorine. Then you look at the periodic table, and you count over there. 1, 2, 3, 4, 5, 6, 7, 8. How many would fluorine have when we do the proper count? 7. We're going to make 1, 2, 3, 4, 5, 6, I don't know, 7 dots, because it has 7 valence electrons. There's going to be a whole lot of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 1, 2, and then I don't know why you keep actually doing the tone in your head, but you will. And you count your way over there. Most of the time when we make these bonds, we're looking for 8 electrons like most noble gases, unless that element is really close to helium. What are some elements that are nearby helium in terms of the number of electrons they have? Lithium and beryllium and hydrogen. Those are the 3 that kind of follow this rule. Lithium, use that dot, beryllium, and hydrogen. And beryllium actually doesn't do it, so I should have written that down. Sorry about that. Lithium and hydrogen are really close to helium, and they're happy to get to 2. Beryllium falls is one of the weird exceptions for it. If they're sharing the electrons, they're called a bonding pair. If there's electrons that aren't being shared, really fancy name for it, unshared pairs. If they're not being shared, they're called unshared pairs or lone pairs. But notice they're pairs. They're not electrons that are lone, they're electrons that are in pairs. They're never apples. Okay. All right. Let's actually just do a couple. In the notes, there's a really annoying 5-step method for doing this. I despise this method. I only teach this method if you don't understand the easy method, okay? So after we go over the homework next class, and you're like, I'm just not getting it, you need to come to me and we'll go through the 5 really slow steps that work every time, okay? So we're gonna hop right, the answers are already on there. Let's just delete these. Yeah, no one sees them, right? Good. Delete. Okay, so we are going to do a molecule here, and I can just make up any one I want because I'm in charge. SF2. Okay. No. Screen just froze.
Oh, no.
Okay, for those of you playing at home, I don't know what's about to happen from your side. I don't know if it just froze. Oh no, my computer's like locked up. I can't click on anything. It's just ignoring everything I try. Oh, I hate doing this.
No.
We start off by finding the elements on the periodic table and figuring out how many electrons they have. Let's find sulfur. 1, 2, blah, 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 blah. How many electrons does sulfur have?
6.
Go to the bathroom. Yes, it has 6. How many does a fluorine have?
7.
7. So this is usually occurring in your head. You don't usually write these numbers down. You usually go, sulfur has 6, fluorine has 7. Who needs more to get to 8?
Both of them.
So that's the first piece of logic, is you just look at them and go, sulfur's going to need more help. I'm going to put it in the middle of the fluorines. It's going to need to make more connections to get to 8 than the fluorine will. So we just write those 2 down, or we hold them in our head so we can figure out who to put in the middle. The neediest element goes in the middle. That's why we have those people right there. And we have the other less needy people on the outside, okay? None of them were looking. They didn't see that at all. I think, as far as I think, you're the only one that saw it. And then we put the electrons around them. 1, 2, 3, 4, 5, 6. Mr. Murphy. Yes, Luke. I noticed that you put that single dot here next to the fluorine. Was that purposeful?
It's not very.
I think.
Lo siento.
When we put the single dots on, we want to consider that they're going to be connected to the other atom, that they're going to be shared with the other atom. So I put the pair on the top and the bottom so they're not in the sharing position. I put the single electron next to the fluorine so they could easily share with them. So how many bonds, how many more electrons does fluorine need?
1.
Only 1. So when this fluorine connects to that sulfur, they're sharing these electrons with each other. Those electrons now count for both atoms. The fluorine now has 8 because of the sharing. And on the other side, this fluorine is going to also share with the sulfur. Are both fluorines at 8.
Yes.
And the sulfur is now at 8. Also 8. The bond counts for both. All right? This is what we're doing, is connecting dots to try to get to a couple of numbers. Most elements are hunting for 8. The elements around helium are happy when they hit 2. There are going to be some exceptions, but not too many. Let's try another one. Let's try SiO2. Starts off again by finding the 2 elements on the periodic table, either jotting it down or just holding it in your head. How many do each of them have before bonding? We will go Lindsay, Chem for silicon, into Ace, who tried not to make eye contact, for oxygen. Lindsay, what does silicon have when you do the fancy goofy count?
4.
4. And Ace, what about oxygen? 6. So who is needier?
Silicon.
We're going to put the silicon in the middle, put the oxygens on the outside. How do I know how many oxygens to put? Look at the formula. How many oxygens are in this formula? 2. I can't tell you how often. Like, one of you's going to do this. Let's just go ahead and throw Arjun under the bus. It's got to be water on the test. It says H2O on the test. The formula is H2O. And then he goes O, H, O, and then tries to connect 2 O's to a single H instead of the other way around. Somebody always does it. They have a dyslexic moment, and they can't figure out how to connect it together because it doesn't work. Right? That happens all that we can't do. O, H, O. So we have the silicon in the middle with how many dots? 4. I'm going to put them all spread out so that I can easily access them without having the other dots in the way. Oxygen, a 6. So that's going to be a couple of pairs. I don't know if you picked up on this. I'm kind of like doing north, south, east, west, putting dots on the north side, the south side, the east side, and the west side of each element. And then if there's pairs, you're trying to keep them as so they look like pairs. You're not just doing like, you are trying to draw the dots in pairs. Who can tell me about Hund's rule or the Pauli exclusion principle? In the Pauli exclusion principle, electrons could occur in pairs of 2, but they had to have opposite spin. These are electrons in an orbital in a pair, but thankfully we're not trying to indicate the spin. We're just putting 2 dots. We're pretending that they're in an orbital there, okay? So we got all our dots down. Now we make some connections. Who's the neediest?
Sulfur.
The elements in the middle. Sulfur, right? No. Silicon. So make that connection to silicon. Make a connection to silicon from both atoms. And then I back up and do a reassessment. If silicon needs the most, you're going to probably make multiple connections to the silicon. Where is silicon right now? 6, which is still not 8. What about the oxygens?
They're at 7.
They're at 7, which is also not 8. If you're at 7, how many more do you need?
1.
So we have to make another connection. There are 2 bonds between the oxygen and the silicon. And there are 2 bonds between the oxygen and the silicon. These are called double bonds. Double bonds. These are called single bonds. The most you can do is triple bonds. Quadruple bonds don't exist. As the 4th bond forms, it breaks one of the other bonds. So you can't actually do 4 bonds together. Even if on paper it works, in reality it doesn't. 3 bonds is the max. Okay? So, where does it start again? You find the elements on the periodic table, and you look and see how many they have. You put down the dots, putting the neediest element in the middle. Sulfur needed more bonds, we put it in the middle. Silicon needed a lot of bonds, we put it in the middle. So we make connections, trying to get them to 8. I'll get rid of the sulfur one because we just did that one. Take a look at this germanium one that's already worked out. Do you agree with that germanium one? How many would germanium have?
8.
Wait, before it gets started,
No,
germanium
4.
has 4. And so it needs how many bonds to get to 8?
4.
4. A couple of rules though. When this electron is shared, it can't also be shared by another one. This electron can only be shared between 2 atoms. It can't be just like, you can't come play with our electrons, ours. Okay? If she wants to play with an electron, it needs to be with a new, fresh electron. We need a new thing over there. Ooh. Let's draw cyanide. Cn -1. Let's draw cyanide. Oh, that's not what I thought it was. That's not what I thought it was. So cyanide is Cn -1. What is, we go to the periodic table, we find carbon, we find nitrogen. There's only 2 of them, so put a carbon down, put a nitrogen down. That part's easy. Figure out the dots there. Anna, how many does carbon have? And Ariana, how many does nitrogen have? Both doing the fancy count right now. 4. Okay. I'll make 4 dots on your behalf. And the nitrogen?
Wait, how far is the 2 go?
All the way until you get to boron.
Okay. Wait, what am I looking for?
Nitrogen.
So 2?
Yep, 1, 2, and then it picks up again when you get to boron, 3, 4, 5.
I'm so confused.
It's 5.
I need everyone to know, not just you and me.
Oh wait, so you start here and you have to go under there.
Yeah.
So 5.
Yeah. So I got my first 4 down. Where do you think I should put the pair, the last dot for nitrogen?
On the right.
On the right, so it's out of the way, yeah. I don't want it to get in the way of all the fancy bonding it's going to need to do in a second. Solomon, if nitrogen has 5, according to some people, how many more electrons do you think it needs? 3. Right, because that's how far 5 away is from 8. This is the really difficult math we're doing in this chapter. Ask her how to go.
Good. I just have one question about the first thing.
The very first question?
Yeah, so both of them are covalent. So
Which of the following is covalent?
yeah, and wait, no. I was doing that wrong.
Okay,
Okay,
yeah,
I'm just gonna finish this up.
Yeah, okay, yeah. So we start bonding. 1, 2, 3. Oh, let me do it wrong just to catch some people right now. Do not do this. Don't go. This bond here doesn't actually have the electrons in it. Okay? The bond has to include the electrons. You need to get water. I will let you go. You're going to pass down the hallway. I'll send it over.
So Murphy, do I put
Tell me
them?
if it doesn't have it. It doesn't have it.
Should I
Put it over there somewhere by that. Okay, is everyone happy in this one?
No.
What do you mean, no? 5. Who's not happy in this one?
Carbon.
What does carbon need still?
1 more electron.
What does that mean, -1?
There's an electron.
There's an extra, which I, at this level, usually teach you to make the extra ones look like this. You are a jerk and I hate you.
Did it crash?
They know. I make them as an X. all right? I make the extra as an X so that I know where I put it. Does that make sense?
Yes.
How did I know there was an extra one based upon the negative one? How many negative ones were there?
One.
So you only got to add one extra. Don't be like, I'm going to add 7. That will fix everything. The formula tells you how many you can add. Like in phosphate, how many can you add? You can add 3. In total, you can put those 3 anywhere you flip and want to. You're a jerk and I hate you. So, as I was trying to say before the internet hated me again, what I would typically do with these is I would make an X to represent that one extra one. If you had phosphate's PO4 with a -3, that means you get to make 3 X's anywhere you want at the end. Do all of the basics. Put a phosphorus down. Put the 4 oxygens down. Put the basic dots. 5 for oxygen. 6, 6, 6, 6 for the 5 for phosphorus. 6, 6, 6, 6 for the oxygens. Make some connections. See what you can do, and then go, oh right, X, that fixes that problem. X, that fixes that problem. X, that fixes that problem. So you add them near the end. Are there going to be exceptions? Heck yes, there's going to be exceptions. Exceptions we will deal with. Boron, beryllium, and phosphorus and sulfur. Let's just jot them down in one spot. So hydrogen was happy when it got to 2. Okay? We're going to make like all of the exceptions in one little column. Beryllium is happy when it gets to 4. Boron is happy if it gets to 6. Most elements are hunting for 8. And then phosphorus or sulfur, P or S, could be 8, 10, or 12. Ew. How do I know what to do? Good question there. Why am I forgetting your name today, David? I keep wanting to say Devin. I keep wanting to flip the V and the D, which is really confusing. We'll just call you Devin. So Devin, when you're trying to do a phosphorus or sulfur, you'll start off by trying for 8. That's the standard move. When that falls apart, okay, I can try 10. If that works, you're done. Like you just try to get the connections so that it equals 10, or the connections so that it equals 12. Like this sulfur one here, sulfur hexafluoride. Sulfur has 6. And it's going to connect to those 6 fluorines. How many would it have after it connects to 6 fluorines?
12.
And that's okay for phosphorus or sulfur. They are allowed to go way beyond 8. All right? And there'll be fluorines on the outside of that. The other stuff we are doing comes with what are they called? The 5 VSEPR shapes, or molecular structures. They are 3-dimensional shapes that represent these molecules. They're very common all over the place in your body and the world around us. I've already introduced their names. Linear, guess what linear looks like?
A line.
Bent, looks like a line, but it's
Bent.
wow. Trigonal pyramid is a triangle that's a tiny pyramid. See, it's like a little tiny pyramid.
Yeah.
Okay, and then I've got, let me do, here is trigonal, but it's flat, so it's all in one plane. And this one's called trigonal planar because the atoms are all on the same plane. Does that name make sense?
Yes.
And then the last one I've shown you a couple times is called tetrahedral. Tetra means 4, just like in the game Tetris, where every game piece is made of 4 blocks. It's in 4 directions. And so when we try to figure out the shapes of things, we almost always draw it first. So chlorine has 7. Beryllium has 2. How many does chlorine need?
1.
1. How many does beryllium need? It's on the list of cheaters. Yeah, it needs 2 because it's on the. It only needs 4. So we put beryllium in the middle with its 2. The chlorine's on the outside. Connect. You don't have to make sound effects, but I enjoy it. It's kind of obnoxious during the test, though. Like, Cam's back there, pew, pew, connecting dots. After a while, Brooke looks at her like, shut up. How many directions is the beryllium going in?
2.
2. Does the beryllium have any lone electrons sitting on it?
No.
No. This is the key to linear, is that you have an atom in the middle, and the other atoms are just in opposite directions. What angle would you say that those 2 bonds are at?
Straight down.
180. Yep. This is a 180-degree bond angle. They're as far apart as they can be. If there was a pair of electrons on here, I'm just going to cheat and pretend this is a pair of electrons. If there was an extra pair of electrons on here, it would push the bonds away into an angle.
No.
But these electrons don't exist on there, as you can see, on the floor. And so they maximize the distance at 180. All right. Ooh, bent. Let's draw water. How many hydrogens should we make? How many oxygens should we make?
1.
All right. Oxygen has how many dots? How many valence electrons? 6. Oh. Hydrogen has?
1.
And then we connect them, and we connect them. How many directions is the oxygen going in?
2.
2 directions. How many extra pairs are on oxygen? 2 pairs. 4 electrons is 2 pairs. So this is the bent shape. If I put extra pairs of electrons on here, it's going to repel them away, okay? And the way I've got it right now is the wrong shape. What are the angles between electrons, 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 and electrons? 90 on this shape here, which is the wrong shape. They're 90. If we could get them farther apart, would the electrons move to the maximum distance or the minimum distance apart? Maximum, because they're electrons and they hate each other. So, shift models. So I put one on. These are the 2 hydrogens attached to the oxygen. This is a pair of electrons. That's a pair of electrons. Now they're all about 108 degrees apart, which is more than 90. Now it's hard to see 108, isn't it? It's more than 90, but what the heck is it? This one says obtuse. Nice. This one says 105. Yeah, it fluctuates between 105 and 109. But bent, you could have drawn this like this. I think it kind of looks like a TIE fighter when you do it like this. Star Wars reference for 5 people. 5 good people, though. That's the same drawing. That's still a correct answer. But that is still 2 directions and 2 extra pairs. When Mia draws it like that, it's like she's looking at the model like this. She's looking at it like that. So she's like, electrons, bonds. Or maybe like that too, right? I was just looking at it like this. It's still the same model, it's just rotated around. This is a weird chapter because some of you are really good at imagining things in 3 dimensions in your head, and other people are like, I made a line in my head, you know? For the people who are great at memorizing or visualizing in 3 dimensions, this chapter, the 5 shapes, are pretty easy to see. The other guys might have to memorize this stuff. 2 directions, 2 extra pairs, it's bent. And when they draw it, they then go 2 directions, 2 extra pairs, it's bent. While the person sitting next to you goes, oh, it looked like this, and this like object appears inside their head. And they're like, and I can turn it around and stuff. And other people are like, shut up. Damn, why are you making those noises? I don't know. I don't know why. Same reason that I pretended that Cole was weaker than Justin. It's not true. Look at Justin's arms.
Yep.
So, let's try trigonal planar. We have boron. Boron is on the cheaters list. Boron does not go for 8. How many does boron go for?
6.
6. So we put boron in the middle. It has 3. It makes a bond to each of these chlorines. I feel like the computer's going to crash at any second. What's fun is that people watching this tomorrow don't actually get to hear the anger in my voice when the computer crashes. They just get the pleasant, it's back now. They also don't get to see the action that occurs. Bond, James.
Oh, yeah, we got it.
Okay, so how many directions is the boron going in?
3.
Does the boron have any lone pairs on it?
No.
So the trigonals are pretty easy to identify. They go in 3 directions. How am I going to tell between the planar and the pyramid the extra pair? If it doesn't have an extra pair, they'll spread out to a nice flat shape, all on one plane. All right? Call it the delta or the united plane. Not that good. I was actually wishing I hadn't said it. Nope, that's not it. Oh, it's in my hand. I was like, where's the one I'm looking for? Boom. 3 directions, flat. Good. We almost out of time. We're pretty close. Not too bad though. Okay. Trigonal pyramid, nitrogen to a hydrogen, to a hydrogen, to a hydrogen, extra pair. 3 directions, 1 extra pair. If I put that extra pair of electrons on top, what's that pair going to do to the other bonds? Who knows what that is?
Sounds like the same.
What was the question?
If you put this extra pair of electrons, what's it going to do to the bonds?
It's gonna repel them.
It's going to repel them, and it's going to make them back into that tiny pyramid shape, where on top of the pyramid, there's just a pair of electrons sitting there, pushing the others away. So it's a triangle pyramid. Cool? There's other fancy shapes in AP chemistry. Oh, wait, one more. Almost forgot about it. We got the tetrahedral. How many directions is the carbon going in? Does it have any extra pairs on the carbon?
No.
No. So it's 4 directions, no extra pairs. On the 2-dimensional screen, what are the bond angles on the 2-dimensional screen? 90s. But these aren't 2-dimensional objects. These are 3-dimensional objects. And when it spreads out into 3D, that angle's 109. Okay? I think memorizing the angles is annoying, but also kind of required. So, we have a couple more things after that, but they will not impact your ability to do the homework. So we'll pick them up next class instead, okay? Guess what your homework is?
Worksheet 1.
Oh, stop being so good at stuff. Okay.